Hi guys, Rod from Bensonium Thought Videos here, and this is the 7th video in my series examining the underlying philosophy that gives rise to the scientific method. So in this series we are examining the tools that power the scientific method, particularly focusing on mathematics. We are also following a very narrow path, developing the mathematical tools necessary to prove Einstein's famous equation E equals mc squared. In my last video, we proved Pythagoras' theorem, and this week we shall use the theorem to begin our journey into what is known as the special theory of relativity. It is this theory that will finally give rise to our E equals mc squared equation. Note that there is a lot of algebraic manipulation this week. In past videos, when I perform an algebraic expansion, I break the calculation into minute steps. This week I shall not do that, but assume you are comfortable with the rules governing, say, expanding a plus b times a plus b. If you're not, then please watch my two videos that precede this one, which are included in this video's description below. So if you have never learnt about the special theory of relativity before, at first it will seem very strange. And yet, despite the fact that we are about to enter an area that is completely outside of our experience, the theory is not only logically coherent, but is also correspondent with reality, being proved many times through experimental observations. So in my second video on the scientific method, we were examining the presuppositions that constitute the foundations on which we build the practice of science itself. The first four presuppositions I presented were summarized by single words all starting with the letter C. These four presuppositions were coherence, coexistence, correspondence, and conservation. The last one is the idea that our universe is governed by unchanging laws that are conserved through space-time. This is an important assumption because if it did not hold, then the practice of science would become impossible. Yet, as discussed in my second video, working out what entities in our universe are subject to change and what entities truly constitute invariant laws can be a bit tricky, because there are entities in our universe which can change, yet are subject to more fundamental laws that are space-time invariant. Now, an important principle of our conservation principle is that the laws of our universe should not depend on our relative motion to other objects in the universe. This last point is important because if we were to exist in a universe where there was only ourselves and one other person who was moving towards us at a constant velocity, quick, please get here, I'm so lonely, then either person in this empty universe has the right to claim they are stationary and it is the other person who is moving because there is no preferred frame of reference. The only reason we think of things being absolutely stationary or moving on Earth is simply because we define the stationary reference frame as the Earth itself, and once we do that, it becomes easy to then say something is at rest or in motion relative to the Earth. Now, when we think of two objects moving in relation to one another, we are used to the idea that the speed of a third object will be different for those two objects. For example, take three random objects, say an angry parent, a naughty child, and a bloke called Bill. The naughty child and Bill are both riding an airport travelator, but the naughty child has decided to walk the wrong way up the travelator at a speed that exactly matches the forward motion of the travelator. Bill is also on the travelator trying to get to the gate to board his aircraft. Now, the naughty child causes Bill to move out of the way to avoid colliding with the child who is walking in the wrong direction towards Bill, who, like the good fellow he is walking in the right direction. Yet the parent who is standing on the floor next to the travelator can remain completely still and shout at the child to turn around because the child, in relation to the parent, is not moving at all, since the child's walking speed is exactly matched by the travelator's forward speed. Given that adding and subtracting relative velocities, as we have just done in this travelator example, is something we experience in everyday life, We are comfortable with what is happening here. Yet we now need to turn our attention to light itself. The first thing we can ask is, what is light? Well, in the 19th century, scientists were playing around with both electricity and magnetism, which appeared to be two unrelated fundamental forces of our universe. However, it was then observed that a changing magnetic field could induce an electric current in a wire, while a moving electric charge in a wire could induce a magnetic field. It is these two observations that give rise to wind turbines and electromagnets, respectively. James Maxwell took these observations and was able to link electricity with magnetism in the form of two second-order partial differential equations, which are now shown on the screen. From these equations, Maxwell realized that if a changing magnetic field generates a changing electric field, and vice versa, then both events would create a self-sustaining feedback loop. As he thought about this, he realized that this reinforcing, repeating behavior should result in some form of a wave, and using his new mathematical equations, he was able to calculate a speed for his electromagnetic wave. The speed he calculated was incredibly fast and would be directly determined by the inverse square root of the product of the two fundamental constants, named the permeability and permittivity of empty space accordingly. Maxwell realized that this electromagnetic wave propagation was actually light that we see all around us. Now, given that the speed of light was determined by these two fundamental constants of empty space, and that there can be no preferred non-accelerating reference frame, it follows that the speed of light should be constant no matter what an object's motion is relative to another. To make this statement even clearer, Einstein imagined a scenario where he was travelling at the same speed and in the same direction as a beam of light. He argued that if the light beam's speed was dependent on the motion of the observer, as it was with other earthly objects like our naughty child, then travelling at the same velocity as a light beam, in more poetic language, Einstein imagined what it would be like to ride a light beam, that it would result in the light beam being frozen in space. Yet if this was the case, there would be no changing electric or magnetic fields in that frame of reference, so the light beam itself could not exist, because light exists in the first place precisely because of the changing electric magnetic fields, as Maxwell's differential equations state. It was this realization, along with Maxwell's equations containing two fixed constants that determined the speed of light, that made Einstein realize that the speed of light must be constant as measured by every observer, no matter what their motions are relative to each other. This theoretical insight also agreed with experiments on the speed of light that were conducted by two physicists, Michelson and Morley, in the late 19th century. These experiments, which measured light speeds at different times of the year and on different parts of the Earth, all confirmed that the speed of light was an invariant quantity. Yet incredibly, for the speed of light always be the same value, no matter whether you measure it on Earth or on board a spaceship travelling at 87% the speed of light, means that space and time must change between the different non-accelerating reference frames, as we shall now demonstrate. So let's begin with the diagram that is now on the screen. Here we have a spaceship with a light clock in it that consists of two mirrors situated 1 metre apart, with a light beam that travels between the two mirrors, forming a ticking clock. We can see that the time t0 for light to go a complete circuit from the bottom to the top mirror and back again is simply 2 divided by the speed of light, which is just 2 over c. We now look at the exact same tick-tock of our light clock from the perspective of someone on Earth who sees the spaceship travelling at speed v. We can see that the path the light takes is a big equilateral triangle, with a base distance being the spaceship's velocity times the time elapsed in the stationary observer's reference frame. We label this vt. Likewise, the height is still simply 1 meter. Now half the path forms two identical right-angled triangles as shown. If we now focus on one of these triangles, we can relate the length of each of its sides using Pythagoras' theorem, which we proved in the last video. So Pythagoras' theorem states that the hypotenuse squared of a right-angled triangle equals the sum of the squares of the other two sides as shown. So we now get a half CT all squared equals a half VT all squared plus 1. This is the same as 1/4 C squared times T squared equals 1/4 V squared times T squared plus 1. Taking out the common factor of a quarter and rearranging, we get a quarter, open brackets, C squared minus V squared, close brackets, times T squared equals 1. Rearranging to solve for T, we get T squared equals 4 over C squared minus V squared. And taking out C squared as a common factor in the denominator, we get T squared equals 4 over C squared, open brackets, 1 minus V squared over C squared, close brackets, which we can rewrite as T squared equals, open brackets, 2 over C, close brackets, all squared, divided by 1 minus V squared over C squared. Now the numerator, 2 over C, remember, is just the time it takes for light on the spaceship clock to make it a full circuit from the bottom to the top mirror and back again, which we labelled as T0. If we finish our solution by replacing 2 over C with T0 and square rooting both sides, we get T equals T0 over the square root of 1 minus V squared divided by C squared. The factor 1 over the square root of 1 minus V squared divided by C squared is given a special Greek letter gamma, and it appears in many equations of relativity. If we rewrite our equation using gamma, we just get T equals gamma times T0. Note I have put this equation in purple as I want you to remember it. Now this equation, while correct, only applies in terms of the way we set up the experiment, where our stationary and moving observers were at the same spatial location. Later in this video we shall develop the more general equation, which is known as a Lorentz transform, and show that in the special case where both the moving observer and the stationary observer are at the same place, we get back to our purple equation. Now before we leave this equation, you might have noticed that the gamma factor came about precisely because the distance light had to travel in the stationary reference frame was greater than in the spaceship. This means that not only does the travelling observer experience less time on the spaceship, but distances along the direction of travel are also contracted relative to a stationary observer. We shall develop the Lorentz spatial transformations later in this video. But for now, let's start working with our time dilation formula. Imagine that the spaceship is travelling at 86.6% the speed of light. In this situation, we get T equals T0 divided by the square root of 1 minus 0.866 squared, which equals 1 minus 3/4. Thus, T equals T0 divided by the square root of a quarter, which means that T equals T0 divided by a half, or T equals 2T0. So 1 hour on Earth, which in the equation is T, equals 30 minutes on the spaceship travelling at 86.6% the speed of light. So why don't we notice time dilation? Well, simply because the speed of light is so stupidly fast. Let's now use a more terrestrial example. Let's imagine you spent your whole life of 80 years travelling on a Concorde at twice the speed of sound, which is 686 meters per second. Now, the speed of light c is 299,800,000 meters per second. So plugging in these numbers in our equation, we get t equals 1 0.000000000052358 t naught, which means that in 80 years travelling on a Concorde at twice the speed of sound, you would only experience 7/1000ths of a second less than you did if you remained stationary on Earth during the same time period. And this is why we never experience time dilation through our lives. Now, something that is important to realise is that time dilation is reciprocal, precisely because there is no such thing as a preferred reference frame. Thus, as long as neither observer is accelerating, both are able to claim that they are the stationary observer and it is their partner that is in motion relative to them. This means that the time dilation formula applies equally, so both observers see time dilate for the other person that is in motion relative to them. Now, at first this might mess with your head, but it really isn't quite as odd as you might think. For starters, we are used to this idea in a different context, to do with the size of objects at a distance. If you are driving in a car and you notice another car in the far distance, that car to you looks small, just as you to the other car also looks small. Yet you might be wondering, but if both observers see each other's clocks going more slowly than their own, how does this work when they compare their clocks at the end of the journey? Well, the relevant question here is, where are the two observers at the end of the journey? If they are now physically separated by a vast distance, then their comparisons are also separated in time because of the finite time it takes light to travel between the two observers. For example, Jack and Jill were twins, and Jill flies to a star 10 light years away at 86.6% the speed of light. It takes Jill, in Jack's time frame, 11.5 years to complete the journey, but due to time dilation in Jill's time frame and also length contraction, it only takes a little under 6 years. Once Jill arrives at her destination, any signal she and Jack send each other will be 10 years in the past when it is received by the other twin. In other words, the light we see from Jill's star are of events that occurred on the star 10 years previously. However, in the formal space-time sense of special relativity, this is the star's current present, because anything happening before light has had time to reach us is not causally connected to us. Therefore, from a physics perspective, such events may as well not exist, for they cannot affect us in any way. What about if Jill flies to that distant star and then comes back to Earth, so she is reunited with Jack? Given the claim is that both clocks along their journey went slower in relation to each other, both twins should now be younger than the other, which of course is completely impossible. This supposed conundrum is known as the famous twin paradox, and because it appears to threaten the special theory of relativity in relation to passing the coherency test of logical consistency, it is often used by those who don't like the implications of the theory to try and demonstrate that Einstein must have been wrong when he proposed the theory. However, as we shall soon see, the twin paradox is not a paradox at all, because it turns out Jill will experience less time than Jack, and so be younger when she is reunited with him. We shall see why this is so in the remaining derivations of the Lorentz time transformations, which we shall now examine. So we are now going to introduce what is known as a Minkowski space-time diagram, as shown. In the diagram, we have time in seconds on the y-axis and distance on the x-axis. If you are stationary, then your trajectory is along the y-axis and your speed is simply the passage of time in seconds. However, if you are moving along the x-axis at a constant velocity, then your trajectory becomes a line moving up in time and out in space, as shown in the following figure for the red car travelling at 1 meter per second or 3.6 kilometers per hour. Now, if we want to transform this diagram so that we enter the car's reference frame, where the people in the car see themselves at rest, we need to perform some form of rotation of our diagram, as shown now in the figure. Now, a pure rotation will not work, as this would clearly stretch out time. Instead, we want to use a Newtonian linear transform, where the distance at each point is returned to zero by subtracting the distance travelled at that time point. The distance travelled is just the velocity of the car multiplied by the time point, so the correct transform is d prime equals d minus vt. Likewise, if we want to go from the people in the car's reference frame back to those observing the car, we must perform the opposite operation. In other words, d equals d prime plus vt prime. Now on this scale, light is so fast that it will just appear to be running along the x-axis as shown. If we now start to rescale our x-axis towards the distance light actually travels in a second, we see that as the divisions on the x-axis become larger, the slope of our car's velocity becomes steeper and steeper, until once we reach a scale that puts a light ray at 45 degrees on our Minkowski diagram, our car's trajectory is now running along the y-axis, which looks the same as a person that is not moving. Thus, relative to the speed of light, all our earthly speeds are nearly equivalent to being stationary, which is why we never observe time dilation as we go about our daily lives. However, now let's put a spacecraft on the diagram which is travelling at 0.5 c. We now need to create a transform such that the red line is rotated back to the y-axis while maintaining the angle of the light ray at 45 degrees. So is this possible? Well, yes it is, and the way we do it is to squeeze our original axes during the rotation, the opposite function of what happens if we just performed a straight rotation of the axes as shown. This squeeze rotation moves our sublight velocity back to the y-axis while leaving the angle of the light ray in our space-time plot as unchanged. We now compare our new axes to the original shifted ones in blue. And when we do this, we can see that both space and time now no longer line up in a one-to-one correspondence. And this is the origin for time dilation and length contraction that occurs in the theory of special relativity. Mathematically, this transform is just our Newtonian transform multiplied by a scaling factor, which we shall call gamma. This now gives us two new special relativity transform equations, which are identical to our usual Newtonian equations, except they are now multiplied by a gamma factor, which will rescale our original axes onto our new reference frame. So let's now derive gamma using this more general system. We shall now return to our two reference frames, now in 3 dimensions. One is labelled XYZ, while the other is labelled X prime, Y prime, and Z prime. We shall state that the X prime frame is the one in motion to the Earth's reference frame, so the T prime of this frame is the same as T naught in our original diagram when we first derived our time dilation equation. We now imagine a single firecracker that emits a light beam in both reference frames. The rule of special relativity states that both observers must measure the speed of light from the cracker as c. We now take our two transform equations and we can instantly replace x prime with ct prime. The light irradiates out in all spatial dimensions equally, and x with ct, as I have done on the screen. Thus, beginning with our spaceship's reference frame blue equation, we can see that ct prime equals gamma open brackets ct minus vt close brackets, or ct prime equals c minus v all times gamma t, or t prime divided by t equals gamma times open brackets 1 minus v divided by c close brackets. We repeat the process with our Earth's reference frame equation shown in white, and we get ct equals gamma times open brackets ct prime plus vt prime close brackets, or ct equals gamma t prime times open brackets, c plus v, close brackets, which equals t prime divided by t equals c over gamma times open brackets, c plus v, close brackets. We can now equate the blue and white equations to get c over gamma times open brackets, c plus v equals gamma times open brackets 1 minus v over c, close brackets. Doing a bit of algebraic manipulation, we get gamma squared times open brackets 1 minus v over c, close brackets, times open brackets c plus v, close brackets, equals c. With a little bit more algebraic manipulation, we get gamma squared times open brackets c plus v minus v all squared divided by c, close brackets, equals c. This simplifies to gamma squared equals c over c minus v squared over c, or gamma squared equals 1 divided by 1 minus v squared over c squared, or gamma equals 1 over the square root of 1 minus v squared over c squared, which is the gamma factor we derived earlier using Pythagoras' theorem. This now completes our spatial Lorentz transforms, which our earlier derivation only hinted at, and that is that space is also altered as one approaches the speed of light by the scaling factor gamma. From these two spatial Lorentz transforms, we can quickly derive our time transforms as follows. We shall take the travelling reference frame x prime transform and divide both sides by gamma to get x prime over gamma equals x minus vt. We now plug the other transform into this equation for x to get x prime over gamma equals gamma, open brackets, x prime plus vt prime, close brackets, minus vt. We shall now divide this equation throughout by gamma to get x prime divided by gamma squared equals x prime plus vt prime minus vt divided by gamma. And now, given gamma is equal to 1 over the square root of 1 minus v squared over c squared, we can now write x prime times 1 minus v squared over c squared equals x prime plus vt prime minus vt divided by gamma. Now, if we expand the left-hand side of the equation by multiplying our gamma by x prime, we get x prime minus x prime v squared divided by c squared equals x prime plus vt prime minus vt divided by gamma. Subtracting x prime from both sides eliminates this variable, and rearranging for vt over gamma, we get vt divided by gamma equals vt prime plus x prime times v squared divided by c squared. Dividing both sides by v and multiplying both sides by gamma, we are left with t equals gamma, open brackets, t prime plus x prime v divided by c squared. This is the full Lorentz time form equation, converting from the spaceship to the Earth's reference frame, as we did at the beginning of this video. Now, in the special case where both observers are in the same place, i.e. x equals 0, we simply get t equals gamma t prime, or t equals gamma t naught, which is the equation in purple we developed at the beginning of this video. Incidentally, for completeness, the other time transform equation to convert from the Earth observer to someone riding on the spaceship is t prime equals gamma times, open brackets, t minus xv over c squared, close brackets. So we have now developed the special theory of relativity time transforms, firstly intuitively using Pythagoras' theorem to help us understand why time moves slower in a moving reference frame, and then more mathematically using a formal axis transform, which gave us the more general time transform formula, which includes an extra term when the two observers are physically separated from one another. It is this extra term that helps solve the twin paradox in terms of sorting out who has experienced more time when the two twins once again are united. So to finish off this video, we have already said that because both twins can claim they are stationary and the other twin is moving, both will see their twins' clock as moving more slowly as Jill travels away from Jack towards the star that is 10 light years away from Earth. When Jill arrives at her destination, any signals that Jack receives from Jill or Jill receives from Jack will be from 10 years in the past relative to their own time frame, because it takes light that long to travel that astronomical distance. However, Jill now immediately turns her spaceship around and returns to Jack at 866C. On the return journey, do both observers see the other's clock going more slowly? The answer is no, and we can see this using the more complete Lorentz time transform. So Jill is now travelling towards Jack at minus v, so her distance x from Jack is minus vt prime. We now plug this into our time transform equation, and we find in Jack's reference frame t equals gamma open brackets t prime minus v squared t prime divided by c squared, which equals gamma t prime open brackets 1 minus v squared over c squared. But the expression in yellow is just 1 over gamma squared. So we now have t equals gamma over gamma squared times t prime, or t equals t prime over gamma. Or in our original notation, t equals t naught over gamma. So now less time elapses in Jack's reference frame than Jill's. So from Jack's perspective, as Jill's spaceship heads back to Earth, Jack sees Jill's clock now running faster than his own clock. Likewise, by the principle of reciprocity, Jill will also see Jack's clock as running faster. So let's now put it all together. Jack and Jill started with their clocks in sync. When Jill flew away from Jack, they both agreed to send a signal to each other every year of Jill's round trip to her destination star and back. We have already seen that on the outward journey, both twins receive each other's yearly signal at a time later than one elapsed year in their own time frame. However, when Jill flies back to Jack, they now see each other's clocks running faster. If the length of time they see the other twins' time dilation and then time contraction was the same, then when both twins are finally reunited, they would have experienced the exact same amount of time and so be the same age. Yet it is not as simple as that. While it is true that Jack will see Jill's clock running faster, this only applies to signals he receives from Jill on her return journey, because this is when the time contraction was occurring. Yet Jack does not receive these return signals from Jill until Jill's journey back to Earth is about 90% complete. This means that Jack sees Jill's time as dilated for all of the outward journey and for 90% of the return journey, because after Jill has commenced her return journey, he is still receiving Jill's outbound dilated time signals, even though Jill is now returning to Earth. In contrast, while on Jill's inbound journey, Jill is still receiving signals that Jack sent out during her outbound journey. Because she is now rapidly approaching Earth, all these signals look compressed, so from Jill's perspective, Jack's clock appears to be going faster for nearly the entire duration of Jill's return trip. So we now have an important asymmetry, in that in relation to Jack, Jill's clock runs more slowly for 90% and more rapidly for 10% of the trip, whereas Jack's clock, as observed by Jill, runs more slowly for only 50% of her trip and more rapidly for the remaining 50%. This asymmetry means Jill is indeed younger when she reunites with Jack by 12 years, which exactly matches the Lorentz time dilation factor, because the overall trip on Earth took Jill 23 years to make a round trip of 20 light years at 86.6% the speed of light, but only 11.5 years on the spaceship due to time dilation and length contraction. Thus, Jill is now truly 11.5 years younger than Jack, even though during the trip both twins saw each other at some points aging more slowly and at other points aging more quickly. Incidentally, it is also common for folk to say that the symmetry of time dilation is broken because Jill had to accelerate and decelerate at the beginning, midpoint, and end of her journey. But this explanation is also incorrect. The resolution of the paradox has nothing to do with acceleration, but acceleration and deceleration were necessary for Jill to return to Jack's reference frame and spatial position. The real explanation is simply due to Jill occupying 3 different reference frames during her journey, while Jack always remains in a single reference frame. Similarly, the space factor inside the time dilation equation means that in certain contexts, the observer, who defines themselves as stationary, will see the distant traveller's clock as running faster relative to their own, whereas at other times they will see the clock running more slowly. It is just the relative time that the other person's clock is running slowly or faster in the first person's reference frame that determines overall which twin will be older or younger. Now, if you are still struggling to understand the twin paradox, and I'm not surprised because it's quite hard to get your head around, I have put a link in the description below which repeats the Jack and Jill twin experiment with the appropriate space-time diagrams that greatly help to correctly account for the time dilations and contractions that occur during the various stages of the trip. Okay, so that is it for this week. Next week, we must increase our mathematical toolbox by adding the important tool of calculus so that we can finish our journey of showing that the energy of matter is equal to its mass times the speed of light squared. In the meantime, if you like this video, please do hit the like key, and if you want to see more of my content, then please do subscribe to my channel by hitting the subscribe button and the bell notification key below. So until next time, I hope your body and mind are in a good place, and bye for now.